Alrighty, we're on worksheet 16. Hopefully this is going to work this time. I tried recording this and it didn't record last time. What a bummer. Okay, so first, the easy thing. We've already discussed this, but I just want to make sure that you know if you have sine, cosine, any of these trig functions, and you want to know what the period of the function is. So, for example, I don't know, you can have a function over a constant here, another constant here. It doesn't make any difference. Whatever's in here is what's going to cause the periodicity to be whatever it is. So let's say we have 3t plus 4. Okay? What you really care about is this piece. That controls it. But what you can do is just set this equal to 2 pi and compare to where it is at 0. So 0 to 2 pi, you can think of this whole thing as being theta, which is a function of t if you wish. And you want to see how long it takes for that theta to go from 0 to 2 pi. So for example, 2t is equal to negative 4, t is equal to negative 2. So at negative 2, this mess is 0. And then how long does it take to get to 2 pi? Well, 2t is equal to 2 pi minus 4, so t is equal to pi minus 2. And so the period is just the difference between them, or pi. A lot of times this thing is 0 at 0. If it's just a multiplier, that makes it much easier. So I think in your homework, the worksheet rather, you have something, I'm not going to say what it is, but I'm going to put a different number here. Let's say e squared times t. Then what's the period of that? Well, you say e squared t is 2 pi and solve for t. In this case, the period is 2 pi over e squared. Okay? So that's how you find the period. Okay, I may as well not bury the lead. This is what we're going to do over the next however long it takes me to do this video, but I want to actually explain to you why these things are what they are. If you do not care and never want to know why, you can go ahead and do the homework. You don't actually need to know this, but I really hope you want to know this. I hope that this is part of your yearning to understand calculus, is to understand why these things work. And so it's my duty and obligation and pleasure to explain these things to you. So let's dive into that. So let's start off with a unit circle with an angle, and this angle is going to change. It's going to open up in the positive direction because we are sitting on a unit circle. We have this special relationship that the actual length right here of that arc piece is theta. That arc length is the same measurement as the measurement of the angle, even though they're different units, but they're the same value. So one is a length and one is an angular measurement, but they're the same value. Okay? So keep that in mind. Now, you have some kind of somewhere in the first quadrant. I mean, the picture is for the first quadrant, even though the proof works for the whole circle. But this side of this triangle, because it's a unit circle, this is going to be sine of theta, and this side is going to be cosine of theta. Okay? So what I want to do is I want to slowly open up this angle, and I'm going to bring it up to, say, here in my diagram. I'm going to zoom in on this, but I want you to just get an idea first for what is going on here. So we're going to try to see how sine is affected. And you can see in quadrant 1 it's going to increase a little. And if you think about cosine, it's actually decreasing a little when you do that. But I'm going to focus first on sine and figure out what it is. Why is it that the derivative of sine is cosine? Okay, so if I zoom in on what's going on with this blue and this red triangle, I want you to simultaneously hold this idea that the triangle is changing, but it's changing so slowly that it really isn't visible, and I have to over-exaggerate this motion in order to express to you what's actually going on. But the tiny motion is so teensy, teensy, tiny that it barely even shows up. Okay? All right. So we just move this blue triangle into this red triangle. And in this case, theta is still basically theta, but the red one is theta plus delta theta. Okay? So for one thing, I'm going to write theta bar to mean the complement of theta. So theta bar plus theta is going to be 180 degrees or pi. So I'm just going to write this here so we know this is a theta bar. And essentially this guy is going to be theta bar as well. So again, this isn't perfectly true, but it's close enough because I'm saying I'm just wiggling this a teensy bit. Okay? The other thing I'm doing is this gray line here is, you can think of it as the outside of this circle, or you can think of it as the tangent line to that circle, because when you zoom in really close, that is one and the same thing. So you can either think of this as this ray going from the center of the circle outward is going to be normal to that tangent line. So for example, this guy is actually going to be 90 degrees and this guy is actually 90 degrees. Okay? You don't need that for what we're about to do, but it's just helpful to sort of get your bearings on what's going on here. I am going to, however, draw a little line this way and come up with a 90-degree angle there, because that is going to define the triangle, this little triangle that I'm going to zoom in again further, this little yellow triangle, and I'm going to see what's happening with that. Okay, so this thing that I just built was a 90-degree triangle here, and I'm just trying to figure out where all my angles went. So this guy was 90. And actually I meant to say theta plus theta prime is 90, or pi over 2, so please ignore my theta plus theta bar is not pi, it's pi over 2, because I'm looking for complements. And that means that this guy right here is theta, because if this guy is 90 degrees, then these guys have to add up to 90 degrees. That whole thing was just to help you understand why this is what that triangle looks like. So that red piece, this red piece, is actually telling us by how much sine of theta is increasing. That's the increase in sine of theta. So what is that piece? Well, this triangle is the same as this triangle over here, except that it's twisted, right? The x and the y has sort of flipped positions. So this is actually going to be sine of theta. So d theta times sine of theta, and this part is d theta cosine of theta, because this is the radius, right? This is the hypotenuse of this triangle, right? So that's why you have to multiply that in. So what it means is, when we open up theta by the amount d theta, and that's the angular measurement, but it's also the arc measurement, okay? They're two different units, but the same value. So when we open up theta by d theta, we increase sine of theta by d theta times cosine of theta. So written in the standard notation, what it means is, if you have sine of theta and you want to take the derivative of it, it means the derivative is cosine theta. That's all it means. Okay? Now, you can look at the same diagram to understand why the derivative of cosine is negative sine, because if you look over here, you notice that cosine is actually shrinking, at least in quadrant 1 it is. And so it's this distance here is the distance by which it is shrinking, whereas the sine is increasing, right? So that's how it gets the SIGN, the sine. And so what that means is a change in cosine as we move that d theta is a minus sign, but the magnitude is sine of theta d theta. Okay? And that is that. And now I need to explain to you where tangent comes from. Well, rather than reinvent the wheel, we already talked about the quotient rule. So sine over cosine is tangent. So if we want to take the derivative of tangent, why not just take the derivative of sine over cosine? You get cosine squared on the bottom. You get bottom times the derivative of the top minus the top times the derivative of the bottom. Of course, it's negative, so we end up squaring, so we end up getting a plus in that numerator. Sine squared plus cosine squared is just equal to 1, and la-di-da. But it's just a lot easier to say secant squared. It is identical to 1 over cosine squared. So if you're one of those people who hates secant, that's fine. Then the derivative of tangent is 1 over cosine squared for you, and it's totally fine. I won't complain. Okay. Now, next we have to harness the same kind of tricks we used to find the natural log. Now, it's possible that you didn't remember it. It was pretty recent, but you may not have gotten it the first time around. So I'm going to just do a quicker job of it this time. So if you have natural log of x here and e to the x over here, and you have yourself y equals x, just for reference, this one's natural log of x, and this is e to the x. These have to be each other's inverses. Well, if you have a point here, a, b, which I'm going to call, let's say, t natural log of t, then this point over here is going to be right across the mirror from t natural log of t. It could be r e to the r. I just decided I'm tired of using x's and y's. Okay, so in this case, t equals e to the r and r equals natural log of t, but that way you have two ways of saying the same thing, because actually that's what we're up against. We have two ways of saying the same thing, and we want to convert. Now, we know that the slope of e to the x is itself, so this slope is just e to the r, which means that this slope is the reciprocal of that 1 over e to the r. But what is e to the r? It's t. So the slope of that tangent line is 1 over t, meaning the derivative natural log must be 1 over t. Okay? So we're going to do the same exact type of thing, but now we're going to do that with our trig inverse identities. At least I'm going to do 2 of them. I'm going to leave one for you because it's only off by it's almost identical. I'll leave that as an exercise for you. But I'm going to do the arc sine and the arc tangent. Okay, so if you have a sine wave, I'm just going to ignore quadrant 3. I'm just going to look at quadrant 1 for now. And I have myself a y equals x line. And I'm going to do the same trick. I'm going to say, well, there's a point here, and then there's another point here that is related to this. I'm going to say this point is t, comma, sine of t. And that means this other point is going to be s, and it's going to be arc sine of s. Arc sine means what is the inverse of sine. Now, if you have a capital A, it means that you've already agreed which branch you're essentially cutting out of. But I'm not worried about that distinction at this moment. We can cross that bridge when we come to it. Right now, I'm not too terribly worried about it, except that you have to restrict sine function to be, like half of a period before you can invert it. I think you guys get that. So let's move on. Okay. So if we have over here a tangent, so the tangent here, the slope of the tangent line is going to be cosine of t. That means the slope over here, the slope of this guy's tangent line is going to be 1 over cosine of t. But horrors, we have a cosine of t, but we want everything in terms of s. But we know s is equal to sine of t, and so we want to convert everything. Well, we have a cosine. Well, beautiful. We know sine squared of t plus cosine squared of t equals 1. So there's got to be some way out of this mess. How can we express that slope in terms of sine of t? Well, what is cosine? Cosine is 1 minus sine squared. That means, so cosine squared rather. Cosine squared is just the square root of that mess. Okay, but what is sine of t? It's just s. Cosine of t is square root of 1 minus s squared. Okay, so what this means is that the derivative of, I'm going to change my pen color, I think. It's a good time to do that. The derivative of arc sine of s is actually going to be 1 over this cosine mess. And there you have it. No big deal, right? So I'm going to let you do the arc cosine one. It's going to be almost the same, but a negative sign will slip in somewhere. Okay, so you need to trace that through and figure out how that happens. But it's almost the exact same discussion. Okay, and I will go ahead and do the arc tangent for you. Just so you know, tangent, if we want to restrict tangent, we usually go from minus pi over 2 to pi over 2 to restrict tangent so that it is invertible. That is typically what we do. Okay, but I'm going to ignore all the stuff that's happening over there just for simplicity. Okay, so we're going to put a point over here and call it t comma tangent of t. And so there's a point over here called s arc tan of s. But we know s is tan of t and t is arc tan of s. Okay, and since we know the derivative of tangent, we know that derivative of tangent is secant squared, then we know that this guy here, the slope must be 1 over secant squared, but let's not get crazy. We're just back to cosine again, right? Because the reciprocal of sine is, or cosine is secant, and that's why we called it secant in the first place, so it would be ridiculous to call it 1 over secant squared. So we've got cosine squared for our situation here. So we know the derivative of arc tan of s is cosine squared of t, but anyway, what does that mean? Okay, well, all this is well and good, but I forgot the fact that in this formulation it really actually would be easier to just call it secant squared. So okay, you will be forgiven for agreeing with me. But anyway, let's go back to calling it 1 over secant squared of t. Now, if you don't remember this next piece, it's totally fine. But even though I expect that you remember sine squared plus cosine squared equals 1, there are two other identities that look very, very similar. And let's remember how we got sine squared plus cosine squared equals 1. It's y squared over x squared. I'm sorry, y squared over r squared plus x squared over r squared equals r squared over r squared. And so what this means is we could have divided our Pythagorean theorem by anything, not just r. And in the case of tangent, it's x. So we have x squared over x squared plus y squared over x squared equals r squared over x squared. So 1 plus tan squared equals secant squared. That happens to be the one we want, or you could have divided by y squared and gotten 1 plus cotan squared equals cosecant squared, which is obnoxious. Okay, this one's bad enough. Okay, but you have your three Pythagorean identities based off of whether you decided to divide your x squared plus y squared equals r squared. Whether you divide by x squared or y squared or r squared gives you one of those three. Okay, so the question is, if we know what the slope is in terms of secant squared, but we really want it in terms of tangent, well, what is secant in terms of tangent? Well, secant squared, well, it's already secant squared, right? So we can just rewrite this as 1 over 1 plus tan squared of t, okay? And then we know that tan is t, so tan squared is s squared. Okay, so that's what we ended up doing. And so the whole reason we kept it in secant is so that we could we could teleport between tangent and secant squared like that. Okay, so in the end, you know that arctan of s, if you want to take its derivative, you get 1 over 1 plus s squared. And then, of course, you can make that, that letter anything you want. It doesn't have to be s. Okay, and what I'm going to do now is just finish up this video with a couple hints about the worksheet. So one thing you want to know is this graph y equals cosine of x to the fourth. What I am recommending that you do is think about it and guess what it looks like. And then after you think you know, then go to Wolfram Alpha or Desmos and have some kind of computer software graph it for you and see how close you got. So I want you to use the technology, and I want you to use it responsibly. So don't use it, the technology as your first attempt at a problem. Use it to check your work and to refine your intuition. Then you're using it responsibly as it was intended, and you can grow because it's there to help you, as opposed to having it there to hinder your growth because it can do your homework for you. Okay, I don't want the computer to do your homework. I want the computer to help you, advise you on what you're doing so that you're reassured that you're going down the right path. And the last two questions on the worksheet, I want you to just have fun with that and think about that. So I'm not going to make any comments about that. And this concludes this worksheet, and I will see you in class.